Hey guys, Mr. Betts here. In this video, I want to talk to you about Taylor and Maclaurin series for functions. So we've been looking at Taylor and Maclaurin polynomials, which we've been using as approximation for functions in some interval around a center point. And the difference between a polynomial and a series when we're talking about Taylor and Maclaurin series is that it's going to be an infinite polynomial that will be equal to the function instead of an approximation of the function on some interval that could be a finite interval or even an infinite interval, which we'll see with some functions. So let's start this by looking at some geometric series. So remember, a geometric series is a series where we have a first term and then each subsequent term is multiplied by a common ratio. And we know a geometric series is going to converge if that common ratio is somewhere between -1 and 1. And we also know that the geometric series has a sum that is equal to the first term over 1 minus the common ratio, as long as it's a convergent geometric series. Remember, this sum formula doesn't make sense. It doesn't really give us anything useful unless it is a convergent series. So if we take that and apply it to an infinite polynomial like the one on the screen here, this polynomial is not just a power series, but it's also a geometric series. So if we take a look at the terms, each term is the term before it multiplied by x, which means that it's a geometric series with a common ratio of x. So with the first term being 1, as long as it's a convergent geometric series, the sum of this series is going to equal 1 over 1 minus the common ratio. So this is only going to be true, like I said, if it's a convergent geometric series. So it's only going to be true if that common ratio x is between -1 and 1. But as long as it is, then this infinite polynomial is equal to 1 over 1 minus x. So what we have here is a function on the right side of this equal sign that is equal to this infinite polynomial right here. And it turns out that that infinite polynomial on the left is the Maclaurin series for the function on the right. So we can expand this into other geometric series, which I'm going to do this in an example video, but this series on the screen is a geometric series. The first term is 3x, the common ratio is -2x squared, and so we can use that to find a function that this is a geometric series or a Maclaurin series for. We can also do this in reverse. So if we have a function that we want to write as a Maclaurin series, what we can do is we can, in very specific cases, as long as it's in the form of the sum of a geometric series, we can interpret this as the sum of a geometric series. So in this case, this is pretty straightforward. This is going to be the first term. This is going to be the common ratio. And so for x values that are between -1 and 1, this is going to equal, so the first term is 1, the common ratio, we multiply by x, multiply by x, multiply by x, and this gives us a Maclaurin series for this function. Now, we already saw this relationship, but we can get this relationship working in either direction. So we can start with a function that's in the form of the sum of a geometric series, or we can start with a series that is a geometric series and go either way. So for example, in this one, and I'll do this one in an example video also, we can say the first term in a series is 3x, the common ratio is 4x cubed, and use that to build a power series that is going to be a Maclaurin polynomial representation of this function.